Finally, I want to thank and welcome Greg Labbé from BlueGreen Consulting Group. For those of you that were at our technical talks last year, he gave 2 excellent talks last year, and thank you again. Also for accommodating us at such short notice. Okay, and I'll let him just tell us a little bit about, for those of you that don't know him, a little bit about what you do, and then we will launch on the discussion. Okay, thank you.
Thank you.
All right.
Thank you. My name is Greg Labbé, and I want to tell you a little bit about BlueGreen Consulting Group. So first of all, we test all kinds of buildings, from off-grid houses to near off-grid houses, deep energy retrofits of existing houses, vintage houses in Toronto, very historic houses, farmhouses. We test buildings. This is a building we tested on Front Street, doing an air barrier analysis on an existing building. We do airtightness, whole building airtightness testing. It's a building we tested in London. Compartmentalization testing for LEED. This is at the X2. You can see getting close to the top floor here. We're testing 1 Bloor Street. Exciting buildings. I can't wait to get to the top. We just came back from Halifax. We're testing windows there, and tomorrow morning we're testing curtain wall for rainwater penetration. And I'll report back to anyone who cares to know how it's going. So part of the tools that we use are, of course, blower doors. We use duct blasters for measuring duct leakage. Everything to do with performance, that's our kind of thing. So airflow through ductwork. We use infrared bolometers. We do energy simulations for buildings using different types of software. This is Woofy. We test windows for rainwater intrusion and also air leakage. This is in Halifax. We're testing a military installation. This is blast-proof windows. You can see here just the amount of connection that was on the 4 corners of these windows. Pretty interesting building. So the agenda today is to talk about SB-12 and why SB-12. It's a draft in 3 chapters, and I want to remind everyone that it is a draft, but we're not expecting any drastic changes from here on until the day it's published. And if anyone wants a link to the PDF, which is the draft version, I can send it to you or give you a link. That's not a problem. I think it's up on our website, on our blog. So I want to talk a little bit about technical jargon. Hopefully we can get you guys sort of trying to explain what things are. I want to try and make this interactive. I know code can be really dry. I remember taking a number of courses with Mike Leo, and it was like, trying to, sitting in the back row. So, the technical jargon is important because energy efficiency is not going away. It's here to stay. If you look at the latest budget, and we'll talk about the latest budget in Ontario. So we'll talk about the 3 paths in order to get a building permit for a Part 9 house. We'll talk about some crucial details and some trade-offs, and what does the change mean for architects in Ontario. So, and lastly, I just want to also talk about building for the future, because I know that there are some people in here who are building better than code houses. And to those of you specifically, I have an important message that I think you'll find exciting as well. So why SB-12? So SB-12 is basically in recognition that anthropogenic CO2 is causing climate change. That's plain and simple. It is the province of Ontario's response to trying to do more with less energy. And if any of you had the chance to go to the website, the province of Ontario's website, the Climate Change Action Plan, this is a direct quotation here, retrofitting buildings and kicking natural gas. I didn't make this word up. This is on the government website, kicking natural gas. And I'm wondering, what is Enbridge thinking right now? They must be thinking, wait a minute, this is crazy. We're being cornered out here. And sadly, that is the case if we can stay the course. So along the kicking natural gas, so the Climate Change Action Plan Contains several incentive programs targeted at different types of buildings to pay for energy retrofits, installing various technologies, including geothermal, solar power, heat pumps, and more efficient boilers to get rid of or cut back on natural gas. It's an incredible change in tone. I mean, on all levels of government right now, the stars are aligning, and it's pretty exciting to a guy who's been in the energy efficiency business and the testing business for 15 plus years now. 554 million to fund to offer rebates and grants to homeowners, 500 million for energy retrofits and social housing towers, 400 million for schools, hospitals, and universities, 350 million for condos, apartments, and office blocks, and 80 million for heritage buildings. There's a little bit for everyone in this budget, and for the record, the money that is going to be spent is the money that's going to come from the cap and trade system. So it's the money generated from that. It's not for people who are getting nervous, thinking, "Oh my God, our taxes are going to go up." Well, the carbon tax is going to start. So $200 million to incentivize people to buy energy-efficient new homes through a rebate of up to $20,000 for buyers of houses. $20,000 for buyers of houses that won't use natural gas for heating. And I think that most people in this room probably think, wait a minute, electric heating in Ontario is just such a bad idea, right? Because it's really expensive. And it is if you've got a really poor quality building envelope. If you have a superbly detailed building envelope, heating with natural gas is no more expensive than having natural gas and electricity piped into your house. And if any of you guys are interested in seeing firsthand, visiting a number of houses, I can give you addresses and names of people. You can go see houses that are using electric only. And in Oakville, there's a passive house being built here in Toronto. There's a number of them built, actually. They're near passive houses. Certification is kind of is something that's just starting to happen. It's taking a long time in Canada. And of course, I don't know if any of you guys have followed the passive house. There's been a split between Europe and the US. So we don't care which program you follow. The principles are identical. So 1.32 billion to start phasing out natural gas heating in homes and replacing it with electric heat, and potentially expand low carbon electricity supply to backstop new heat pumps and electric vehicles. The province will also offset increased cost of electricity to consumers. Again, this is not language that I'm making up. This is all on the Ontario government's website. All new homes and small buildings built in 2030 or later do not use fossil fuels for heat or cooling. By 2050, this requirement would apply to all buildings. And the building code will also be changed to require all major renovations to improve energy efficiency. This underlined statement is really interesting because there are very few jurisdictions in the world that actually require existing buildings to increase their energy efficiency. The code right now says if you're gutting a house, the performance after can't be any worse than the performance before, right? So you break it, you buy it, is basically what the code says. So there's no incentive for people to increase the energy efficiency of their house. And nor is there a lot of appetite in it either. But in the future, we may probably see a required major renovations will improve energy efficiency. Anyways, it's not in this cycle, so don't worry about it. And of course, like the Toronto Green Standards, municipalities will also have a say and will be able to impose even tougher energy efficiency standards than those contained in the building code. So the drafted SB-12 comes in 3 chapters. Chapter 1 is the scope. Chapter 2 is the 2012 version, and 2015 editions for Part 9 permitted before January 2017. And Chapter 3 is the chapter that we're all interested in today, and that's for Part 9 permitted after December 2016, so the 1st of January. So first is the technical jargon. The world of building science and energy conservation have their own acronyms. So I really feel it's good to be fluent as professionals, that we all be able to talk about, what do these acronyms mean? What is it, how do I measure air leakage? What does that mean to me? So in order to give you that language, I think it's important to sort of talk about things a little bit. So Mechanical, on the mechanical side, we've got water tanks and boilers are usually measured in, okay, who's gonna be brave here and tell me what the EF stands for? Any guesses? It's the efficiency factor, okay? The efficiency factor. So that's how you measure the efficiency of tanks and boilers. Forced air gas furnaces, AFUE. Any guesses what AFUE stands for? Annual fuel utilization efficiency. You guys are either falling asleep or I'm putting you asleep already. I hope that's not the case. So annual fuel utilization efficiency. It's not the standards, it's not a steady state efficiency. It's the efficiency of, it's just like your car. We're saying that includes the efficiency of you starting the car is not warming up, is not warmed up, and that phase of it not being warmed up is also included in the efficiency. So it's the average. It's not the steady state. So the AFU is usually a little bit lower than the steady state. Ventilation, heat recovery, we measure the efficiency of heat recovery ventilators, so ERVs and HRVs with apparent sensible effectiveness, and it basically has to do with the amount of heat that we're recapturing from the exhausting air. Is there too much of an echo? Should I be turning this down here? Is everything okay? Okay. Windows they're rated using what they call a U value. And in the building code, there's also an efficiency factor. And in this iteration of SB-12, all of the requirements in the past version have decreased by 0.2. So in other words, a U value is actually the conductivity of the window, the conductivity of heat, the heat conductivity. So the lower that number is, the better it is at the better it is at not conducting electricity or energy. So you can see here that it's inverse. A 1 would be a superb window, and a 2.8 would be, not a great window. And skylights, incidentally, always rate a little bit more poorly because they're flat as opposed to vertical. If it was vertical, it'd probably perform quite a bit better. Over here, we have a category called the ER rating, the energy ratings. And this was a Government of Canada invention back in the 80s or 90s, where they thought they would simplify things for consumers and give it a simple number, as opposed to having, the conductivity, the amount of solar heat gain that it gets, etc. So they thought they would, but it hasn't caught on. So I'm not sure why it's necessarily here, because you won't find it on the labels for windows anyways. Air leakage is measured in pascals, which is force applied per square meter of area. So it's an acceleration per square meter. And air leakage is measured either by area or rate. So when we take our blower door and we suck air out of a house, we measure the flow rate going through the hole, but we also come up with a composite hole of, well, if I measured the air leakage in this room right now, I can tell you that the composite hole would include these open windows, probably a lot of holes around. So at least the composite hole would be all of the open windows, the area of the open windows. So maybe we would have, about a square meter of air leakage area in this room. So air leakage area at 50 pascals. So again, we're measuring it at 50 pascals of pressure, so we depressurize the building. And this is important because there's a trade-off with air leakage, and it's kind of the last low-hanging fruit for SB-12 at this point. So there's leakage area and leakage rate, again at 50 pascals. So so what we try to do with data, with air leakage data, is we try to normalize it to a feature of the building that we're testing. And we do that either with the building volume, the heated volume, or we do it with the skin surface area. That is all 6 sides of the box. So ceiling, walls, windows, and the slab. It includes the slab. So just remember, all 6 sides. And one of the metrics that you'll see in the tables is what they call an air changes per hour. And basically, an air changes per hour is the air leakage rate normalized into the volume of the house. And they've got an ACH 50, ACH 75, or ACH natural. In this part of the building code, we're using it at 50 pascals, okay? And the leakage rate per hour normalized to the building's heated volume. The air leakage area, the NLA, normalized leakage area, is there's the units for us. So it's 70, based in centimeters square of air leakage per meter square of building envelope, or in inches squared per foot square. And it's normalized to the building's skin surface area, all 6 sides of the box. Compare that to the leakage rate, which is liters per second, or CFM. Okay, so we'll go back to the other one. CFM, so this is in area over area, and this is a rate, CFM, cubic feet per minute, okay, or liters per second. So you can see there's an element of time in that numerator. So window to wall ratio. Who here can tell me how they calculate window to wall ratio? Does it include the garage wall? Any takers?
Sure.
Yes. Yeah, and what about if it's a semi-detached house? Does it include the attached wall that you're attached with? Yes, that's right. You get 2 stars. Thank you. Good. So in the case of the attached garage, the walls that are common with the house and the garage are also included in the calculations. So the window to wall ratio is something that you're going to have to become familiar with and calculate it if you're not already calculating it. For attached homes, the common walls with the other condition units are also included in the wall area. Fenestration areas is based on the rough structural opening provided for the windows, skylights, sliding glass doors, and for glazed portions indoors. Heat loss, conduction versus resistance. And again, the building code really goes into a lot of detail this time. It's pretty surprising to a building scientist, how much detail has actually gone into. And I think it's slowly moving in the right direction. So conduction versus resistance. So you can think of conduction as the ability of the frying pan, the heat in the frying pan coming through through the metal, through the handle, and eventually getting hot. Whereas the pot holder is the resistance of the heat flow. So they're really the yin and yang of the same thing. And you can see here that, again, the building code complicates things here by adding metric and imperial. And there's a ton of tables because of that now. So we've in fact doubled the amount of tables. The continuous insulation, this little CI, you'll see that in the tables. So the little CI stands for continuous insulation. By continuous insulation, we mean taking, if this is your stud, and you've got insulation inside the stud cavity, continuous insulation would be, on the outside, would be the amount of insulation that you're having outboard of the structure. So the building code is really trying to push designers to design with a continuous layer of insulation to get rid of the thermal bridging, so the losses happening at all the studs. There's only one option, path 1 in the tables that you'll see, that gives you the option of not putting continuous insulation on the outside. Nominal versus effective R value. Again, calculating the effective R value of an assembly typically requires software that can account for the thermal bridges and add an air film layer on the inside, on the outside. It talks about in the building code. Again, if we're putting an R22 bat in the stud cavity and we're putting another 10 here, we wouldn't just say, well, that's 22 plus 10 to give you 32. Okay? It's actually a little bit less. And depending on how often your studs are spaced, right? If they're spaced every 12 inches versus 24 inches, it'll make a difference in terms of the thermal bridging. So there are pieces of software that can help you calculate that. Certified energy auditors can help you, we've got the software to be able to help you calculate that. Nominal insulation, there are tables as well available. Nominal insulation is what the bat of insulation comes at. It's stunning. We do a lot of the energy efficiency design summary work for architects, and both at the City Hall and with architects, this is something that has been confounding a lot of people because they confuse the nominal with the effective. We get so many questions, and I don't mean to be belittling here, but it's something that's very important. So nominal insulation R value is when you go to Home Depot and you see the bat of insulation that says R22, that's the nominal. Okay, it's a name only. versus the effective insulation is actually, it includes the extra R values of the sheathing, the siding, the air film here. It includes the drywall. It includes the air film there. And it also includes the conduction through the studs. So that's the effective insulation. You'll see the tables include that ad nauseum. Next is prescriptive versus performance. Some paths are prescriptive, which means follow the recipe and you're home free. Versus performance. And performance paths, they get analyzed by an energy simulation software, and airtightness tested may or may not be a requirement depending on the path that you choose. So what are the three parts, you ask? Well, since the Ontario Building Code has caught up to the minimum of EnerGuide 80, say goodbye to the fourth path, which was in Part 12 of the Building Code. So that option, if any of you guys use that option, we used to use it quite a bit. It was nice and simple. EnerGuide 80, building inspectors, plans examiners, they let us go. It was very easy. EnerGuide 80, you check the box and you're done. So now we're down to 3 paths, and we have less options in our paths or in the tables. So basically, the 3 paths include compliance package or SB-12 prescriptive, performance compliance, or what they call in the code other acceptable compliance methods. I'll have to change that little typo. So in SB-12, we have kind of the do-it-yourself, which is this prescriptive compliance path. It's the least onerous, but the most restrictive. Basically, you choose one of 6 optional paths for the right zone, and you can't be above 22% glazing, okay? And then you get your building permit. The other 2 require the intervention of a building envelope consultant and or a certified energy advisor or a PEng. Those are the people that can help you out. So performance compliance path is front-end loaded, so there's an energy simulation for a permit, most flexible for glazing. So if you've got 40% glazing, it's quite often we can still work with that and make it work. And there's an optional airtightness test, but we'll see why. I'll make an argument for why we shouldn't consider that optional anymore. And then, of course, there's the other compliance paths, which include EnergySTAR and the R2000 program, which are front, mid, and back-end loaded. Typically, the builders that are going for this are Tract developers, big builders who are building 200 houses within 6 months. So this is the existing energy efficiency design summary sheet that you get with the City of Toronto. Every municipality has one. So you check your compliance option here. Next year, this will be the case. It'll be reduced to 3, okay? So you enter in all the specs for the ceiling. You make a promissory note here saying that the RSI value is going to be X. You put in all your specs for all the different parts of your house, the windows, the mechanicals, okay? And then if you've done a performance path, you put in your information here, and then your energy evaluator will sign it and give their evaluator number. How does it work? So the prescriptive path, we'll start with the first path. It's basically, you choose one of the 6 packages in SB-12, design your house according to the said package, and you check for credits. You might be able to swap a few things out, depending on, if you do an airtightness test or, if you've got any other goodies in there. At the municipality, submit your drawings, fill out the energy efficiency design summary, and get your permit. The performance compliance path is a little bit different. Submit your plans. We're back on prescriptive path. Performance path is a little bit different. So yeah, submit your plans and mechanical specifications to a certified energy advisor or your mechanical designer if he's a CEA. If needed, you tweak the building shell to reach the desired level of performance to get a technical report from a CA who fills it out, gives you the technical report, you fill out the EDS, and you go to the municipality to get your permit. It may require airtightness testing if you really had to squeeze the building envelope. And I think with a 15% increase in energy efficiency required for this next code cycle, I think that we'll start to see more airtightness testing. Certainly, I think obviously the governments are talking to each other. The federal government is looking to train energy advisors in doing pre-drywall tests. So that's something that we offer to our clients. We do a lot of pre-drywall testing for our high-performance builders and architects so that they can get the air leakage rate down to a very low level. So the crucial details and trade-offs. What we have is there's a table specifically for electric heat. So just know if you're building an electric heat house, it has to be better insulated. And if you're building an electric heat house, it should be also airtightness tested. One of the things that I forgot to put in here was one of the big changes is also mandatory heat recovery in ventilation. So the ventilation system is the old exhaust fan only, where you can have a principal exhaust fan on the second floor, switched by, right next to, typically you'd see it right there on the, on the main floor next to the thermostat. You'd see a switch, a nondescript switch, an electrical switch that just said fan. And most people didn't know what that fan was for. Well, you'd switch it on and it turns a bathroom fan on the second floor. And that's the ventilation system that we've had prior to 2017. So that's what we can build a house with. That's an acceptable ventilation system. I'm kind of joking, it's not acceptable because it over-ventilates one room and it's not specific enough. I think that we have the technology, and this was kind of a missing piece, was to actually put in balanced ventilation. So whatever you bring in, you pump out your square meter of dirty air, and you bring in a square meter of fresh air. So it's balanced, and there's heat recovery between the two streams. Remember that for electricity, in terms of the this path is used often in Canada for super efficient passive or near passive houses. And like I said, these are houses that are being built right now in Ontario, and we just came back from Nova Scotia. Nova Scotia has a lot of passive houses being built specifically because there's no natural gas. There is natural gas, but the lines are not plugged into every residence. So it's really difficult to get natural gas piped to your house. So consequently, a lot of houses in Nova Scotia are using electricity as a heating source. A little bit more mild. Boy, the rhododendrons are nice there. nice time of year to go to Halifax if you haven't been in this spring. One of the other things too in this part of the code, just like the other one, was thermal bridges. So if you're using 2x4s, wood 2x4s, know that you're going to have to increase the amount of outboard insulation. Okay? And if you're using steel studs, you're going to have to justify that the steel stud is equal in performance to a wood stud, or you're going to have to increase the amount of insulation in the stud bay by 20%, okay? Unless you're already putting in 25% of the total R value on the outside of the wall.
How can you make a metal stud? How can you make the argument that a metal stud is not or less conductive than a wood stud?
Good luck.
Exactly.
Yeah. Yeah, I think that they just put it in there to shut people up, right? It's kind of like reflective barriers. We get the question all the time, oh yeah, I'm going to put this radiant barrier and it's going to add R20. Well, no, it's not going to add R20, So they just put it in there. They said that if you're putting in a radiant barrier, go ahead, put your radiant barrier in, but you're not going to get any claimed R value with it, okay? So yeah, there's a few things where I think whoever's writing the code just has a really wry sense of humor. Anyways, yes, good point. I kind of had to laugh at that, and I'm glad they put it in, because when you see steel, put your insulation one side or the other, but don't put it in between. Trade-offs for airtightness. So this is pretty exciting. This is something that we've kind of been thinking would be a really good idea for a long time. We think that the targets are very low and attainable. Okay, so right now an EnergySTAR house rates for detached. Okay, so these are based on EnergySTAR airtightness levels. 2.5 air changes per hour. See, this is all that boring stuff that we did right at the opening is paying off right now, okay? So you see this now, the normalized leakage area and the normalized leakage rate. So again, this is at 10 pascals because Canadians have to be different than Americans. There's a lot of fighting here between US and Canada. That's all fun to see. So yeah, basically, it's kind of interesting because they are giving you the option of meeting one of these, okay? It doesn't have to be the most stringent. It has to be one of them, okay? So you basically, if you've got a very large house, it's very easy for you to make the air tightness, the air changes per hour that's normalized to the volume, very easy to reach that, okay, in a big house. In a small house, it gets really tough to do. Now, in a small house, this gets easier to do, but in a big house, it gets a little bit harder to do. So, now, trade-offs. Trade-offs as far as air tightness testing, this is what they kind of look like. You know, maximum 1 substitution per dwelling unit. So if you reach the air tightness level that you said you would, either in your, you see, these are the minimums. If you said that we're going to bring it down to 1 air change, and you bring it down to 1 air change, you could, in theory, well, actually, you know, there's no extra credits for it. But yeah, let me back up. If you meet this threshold, any one of these thresholds here, you can swap this requirement for this requirement. So in this table, there's a maximum of 1 substitution per dwelling unit. In this table here, there's a maximum 2 substitutes per dwelling unit. Okay, and you'll see it's a table festival. There's so many tables in this small part of the code that it'll take you a few minutes to sort of get your bearings. So you know, one of the so for instance here, above grade continuous wall insulation, if required R7.5 of continuous insulation, the CI, and or R10 of continuous insulation, you are able to reduce the insulation to R5 and R7 respectively, okay? So those are the kinds of substitutions that you'll see. We're hoping that nobody here really wants to substitute anything because they all want really high efficiency buildings, but it's something that you can credit. Certainly, you know, I think the slab one might be interesting to people. A lot of people seem to think this is very expensive, but you know, if you're going with a radiant in floor, you can't do it anyhow. So this is what a typical table looks like, and you can see that little CI here, continuous insulation. So for example, walls above grade, there's a nominal RSI value. There's a maximum U value and a minimum effective RSI value. So you have to meet one of these, okay? You have to meet one of these. So either the U value or the minimum effective, okay? So, and it's given out by zone, so this is for additions to existing buildings, okay? So this is what a typical sort of table might look like here. So what does the change mean to architects and designers? Well, you know, we can start by saying, you know, well, which is right for me? You know, most designers build homes will likely go for SB-12 prescriptive if they have less than 22% window to wall ratio. Now, who here designs houses with a lot of windows? Okay. Couple, okay. So you're going for compliance path all the time. So you won't be going for the prescriptive path. So, but for those of you who are doing less than 22%, you'll probably be using prescriptive because it's really simple. You can kind of do it yourself. Remember though, if you've got over 17% window to wall ratio, your window ratings need to improve by a U value of need to decrease by 0.2. So here's a typical table for heating equipment that has efficiency of greater than 92% AFUE. Okay, so the tables are basically apportioned for heating systems in imperial and metric. So that's basically you're doubling your number of tables because of imperial and metric, and you're also doubling it because of the zone. Okay. So however many tables you thought you needed, you'd have to multiply that times 2 times 2. So So 92% AFUE or better is the first table. If your heating system, if you're using a boiler for radiant in floor and convective fan coil units elsewhere in the house, then you're using these tables. And if you're going for electric heating, you're using these tables. Okay. So maybe you're somebody who sees a value proposition in getting an EnergySTAR rating. Maybe you like this brand. We find very few custom home builders going for this. This is usually tract builders that are going for this. R2000, this is a really sad story. I don't know how many people here have heard of R2000. So yeah, R2000 was developed in the 70s and 80s. It was kind of somebody, out of the Saskatchewan Conservation House, Enercan came out with this fantastic new idea of having heat recovery and super efficient houses, and they posited that by the year 2000, so many houses in Canada would be R2000 rated. So this was kind of like our Avro Arrow of the energy efficiency world. It never took off. There's maybe a couple hundred houses. It's certainly more popular in Quebec, where there's a lot of electric heat, and it's a lot more popular in Northern Ontario, where there's a few more certified builders. So these, if you see a label opportunity, if you think you can, if you're a spec builder and you think, well, EnergySTAR would really help me sort of jazz this up, then yeah, these are paths that are optional too. But typically, tract builders right now, and we're verging on the 40%. 40% of tract built homes are EnergySTAR rated. So think about that. If you're building a custom home and you're not building better than code, just know that 40% of tract built houses are going to perform better than your house. So if you've got a lot of glazing, if you like that modern look, then you're going to go for the performance compliance. It's a path that offers a lot of flexibility. Basically, it's where you do a performance calculation of the house plan it'll be modeled by a certified energy advisor using an approved software, and the approved software is all listed in the appendix. The energy model credits the house with a solar heat gain through the windows, and there's also insights gained that allow the designers to maximize efficiency and minimize the building cost. And that's when you work with an energy modeler that is experienced, they can help you really optimize the efficiency of the shell, okay? By selecting building materials that might be a little bit less expensive in terms of giving you better R value. You see I've got a bunch of different materials here that are for different sheathing options. We also know how to work the software so that it definitely minimizes energy consumption. In most cases, a tested house performs better than an average, and I say that because the minute you tell a builder that we're going to be testing, airtightness testing a house, they immediately build a better building. They pay a little bit more attention to the envelope if they know that somebody's going to be coming by. So let's review. So path one is the SB-12 prescriptive. It's where an architect designer finds the appropriate table in SB-12, and depending on the zone and heating source, they pick a path. They choose the applicable table and one of 6 possible paths. If using a combo boiler, they use column A4. This is typically what a section of it might look like. We showed you that already. HRV. Some minimum ASE, 75%, 70%. So, there's different options here. And you and your the architect and the mechanical designer can really figure this out in short order. It doesn't take a lot of time. Basically you choose your path, you fill out the form, and you get your building permit. The next one is a little bit more interesting because we're building what we call a reference house, and we're comparing it to an as-built house. And that's done with an approved piece of software. And we're really happy to say that in this latest iteration, they've taken our suggestion and they've included 2 different pieces of software for the passive house, both the European passive house, the PHPP, and the American FIAS standard, which uses WFI Plus or WFI Passive. So those 2 pieces of software are now enshrined in the building code, and barring anyone knocking them out of the draft, I think that we're in good stead. There's a lot of other softwares listed that nobody really uses, so I think there's a good chance it'll stay in. So the evaluator does an energy simulation of two houses, basically two energy models. So we do the house as planned, with lots of windows, and a reference house. Now the reference house is a little bit different, and Chapter 3 explains exactly how the reference house, how you model it. They really break it down for anyone who wasn't sure. If there was ever any question before, there's no questions now. So energy modelers have been doing this since 2012, so we're quite comfortable with it. But essentially the reference house, what we do is we take the reference house and we reduce the amount of window area equally on all sides, so that now we don't have a lot of thermally weak window. We've got a lot more high R value wall assembly. So now the reference house is actually going to perform a lot better than the as-built house. Okay? So what we're trying to do is we're trying to make the reference house a little bit more efficient. Okay? And there's a very specific set of rules you'll see in Chapter 3 that tell you how to set up the reference house. So that reference house spits out an energy consumption per year. Now what we do is we take the planned house with the large windows and we run it through the exact same simulation, and it spits out an energy consumption per year. And that energy consumption, what we do is we play with the energy model, with the architect's instructions. We work with the architect in a collaborative circle or with a mechanical designer, and we say, okay, well, why don't you go with a slightly more efficient furnace, and why don't you add a couple of extra R's on the outside sheathing, and then we'll bump it up to, it'll drop the energy efficiency, or it'll drop the energy consumption just below the reference house, and then bingo, we're done. So if they agree to that, those extra costs, sometimes a little bit of extra cost, then we're good to go. We issue the technical document because the building department wants to see a technical document comparing the reference house to the as-built house. And we fill out the energy efficiency design summary. You get your building permit. Okay? So, but essentially what it's, so it is literally, where you're building a reference house with 22% window to wall ratio, and your as-built house, really the performance of it needs to come up quite up. It needs to come up substantially as a result of the smaller windows on this house. So let's see here. With this, with the same software, the house, so we've been through this annually. Let's see here. Okay. Yes, CA fills out the ADS form, architect takes the report to the municipality, pulls the permit to build. If a more restrictive airtightness test was specified than what's in the code, right, if part of the requirement in your EEDS, you say that you're going to meet a certain level of airtightness, then it's documented. The building inspector will want to see proof that you've actually, that the building pre-occupancy will actually have been airtightness tested by a third party and will be able to meet a certain level of airtightness. Now, if you ask the question, well, what happens if it fails? Well, I mean, we try to make sure that it doesn't fail. We work with builders. So essentially, if you're going to this path, our recommendation is that you possibly do two tests. One is a pre-drywall test. Okay, so before the drywall's on, you should have somebody do an airtightness test where the air barrier is still accessible. Okay, and when the air barrier can still be repaired. So at that stage, it's a very rough stage in the construction process. It's a great chance to pull your builder aside and say, look, this is where your deficiencies were. You need to seal all these places up. We're going to come back in a week. We're going to retest the house, and hopefully we make it. Now, I don't think that any building inspector would not give you an occupancy permit based on a failed test. But what I can say is that if you've designed your mechanical system with that certain air leakage rate in mind, you're really riding a fine line of your mechanical performance not being able to really, on the coldest day, being able to keep up with the heat loss. So there is a small risk in there on the coldest day. It's a manageable risk, I think. But yeah, we work with builders and architects. So basically what I'm saying is if your builder has never had an air tightness test done before, go through the process early. Don't wait till you're about to hand over the keys to the client, because that air tightness test is usually something that everyone gets excited about. We all want to perform. We all want to get that little trophy. You know, we all want to reach our goal. It's very important. So on the third path, EnergySTAR, the path kind of goes like this. The architect designer selects a builder option package, BOP as they're called, from the EnergySTAR tables. So the EnergySTAR tables are not listed in SB-12. It's a different document. You need a builder that is certified. It's the same thing with R2000. Okay, you need a certified builder. You need, and it's a certification that takes a day. It doesn't cost much for the builder. It's not very onerous for the builder. Okay, what will be onerous is getting the test done and reaching the air tightness test. But having said that, you know, we see tract builders making the air tightness test time and again. If tract builders can do it, custom home builders can do it too. So the plans for the house are drawn up following the specification in the BOP. An evaluator does a simulation, an energy simulation on the plans, and if needed, tweaks the design so that it meets the requirements of the EnergySTAR or R2000 standard. Then the architect selects an EnergySTAR R2000 qualified builder. It's 1 day of training. The architect takes the technical report to the municipality, fills out the energy efficiency design summary, attaches the builder option package form, and then pulls a permit to build. I know, everyone laughs at me when I say that. No, it's not that fast. But you get the gist. So just prior to the occupancy, the house gets an air tightness test, and hopefully everything goes okay. With the EnergySTAR and R2000, that's a little bit more tricky because they actually need you to meet the air tightness test. And again, don't play games. If it's the first time your builder's actually air tightness tested a house, get the house tested, you know, a few weeks before in the rough stage when the air barrier is still accessible. We do this all the time with the passive houses, with the near passive houses that we test. Get a magic marker, you're circling things so the builder knows exactly where to go. You're photo documenting, you can make a report, a punch list, whatever you want. The builder knows what they have to do. So yeah, essentially, so just prior to occupancy, the house gets air tightness tested, and client gets an EnergySTAR label mailed to them for the house, and that label stays with them or with the house. So there's, in terms of energy, it's funny because we are now requiring, as of the Ontario government is proposing to mandate energy auditing of buildings. And I wonder if it's a labeled building, if they would still mandate an energy audit of that building. So, because it's a labeled building. So, anyhow, probably. We'll see in the coming year. So, performance compliance. So basically, what I want to talk to you about this next section is building for the future. And, you know, we talk about the 2030 challenge. There's all these big, beautiful ideas, these concepts. And what I want to tell you is that you don't have to wait to 2030. We have the technology now. We can build super efficient houses right now. And so don't wait. And so like I said, now passive house is enshrined in SB-12 in the draft version, or, you know, touch wood. There's already a dozen passive houses or near passive houses in Ontario being built, or in the, you know, built or being built. There's a number of them that are certified. Some of them will be certified. Some of them are near passive houses. So when I say a passive house, they're literally houses that require a hair dryer, the amount of a hair dryer, you know, to heat them. Maybe 1 or 2 hair dryers. And if it's a near passive house, it might take 3 hair dryers. At which point we're kind of saying, who cares, right? It's so close to being a passive house, we call it a near passive house. So there's a lot of super efficient houses built in Ontario right now, and you can visit them. You can go check it out, and it's really a great learning experience. So there's no need to wait till 2030. And like I said, with this $2,000 potential incentive for no natural gas being piped to the house, and like I said, in Toronto, we've seen a couple of these. Solaris, Greening Homes, the builder, Greening Homes, they've built a house where they've cut the natural gas line, but they didn't get the $20,000. But just remember, that could be a very powerful incentive for you and or the homeowner. So these are the softwares that we're going to be using next year, Woofy, which is put together by the Fraunhofer Institute in Germany. They're the ones that came out with the original PHPP software. And this software is really, really slick because it allows us to take a DWG file, import it, and there's no more goofing around with calculating the area of a wall and saying, well, this is wall type 1A, it has this R value, this wall section is this size. We used to have to do that, and literally it was half a day on some of these big houses. So we're pretty excited about this. This is something that finally brings a lot of technology together and will allow us to spend more time doing useful energy modeling. So basically our process for energy modeling in-house and airtightness success basically starts off with a design, simulation, construction, and somewhere towards the end of construction we test. Then there's the operation and maintenance of the building, post-occupancy. And essentially, some of the stuff that we do in the testing and the energy modeling has upstream effects. So for design, it has downstream effects. So the upstream effects are that, we might influence you on the material selection. Maybe there's, maybe the assembly design needs to be tweaked. Maybe we recommend a different mechanical system, a ground source heat pump, or air source heat pump. The efficiencies of air source heat pumps are really amazing these days. And also, the quality control on the building envelope in terms of testing. On the downstream, it's all positive. So the downstream of doing all this planning means that you've got guaranteed energy consumption. So there's no vagaries in that, okay? Because you're testing it. The energy model is pretty good at predicting what the energy consumption is going to be, barring your kid plugging in some Wi-Fi or some big power. You'd feel the heat. You'll feel the heat from all these electronic gadgets anyways in a super efficient house. So, but the benefits are, the downstream benefits are known energy consumption, better indoor air quality, better comfort, better durability, and noise reduction. What's there to complain about that, right? And we really feel that the elephant in the room comes down to this. And so I ask you, what's the difference between these two devices as far as keeping your coffee warm? Right? There's an awesome thermal disadvantage here. This cup is at a complete disadvantage. It's not sealed. It's got a little hole in it, and it's not a double wall. Whether there's a vacuum or not, I don't know, but there's certainly two reflective surfaces in there that are not touching, right? Reflective surfaces can't touch. If they're going to be reflective, they can't touch. Otherwise, it's called conduction. So it'll work in there in that case, okay? So, but this thermos will keep your drink warm for hours. Your coffee, you're lucky if it'll keep warm, depending on how cold it is outside. You're lucky if it'll keep a drink, warm for 10, 20 minutes if it's cold outside. And so we're making the same argument for the house. Why settle for this when we can go for this? So this is the impact here of airtightness, is the orange, the infiltration loss, okay? Again, the air changes per hour, ACH at 50 pascals, air changes per hour at 50 pascals, air leakage in a home. At 1 air changes, 2 air changes, 3 air changes, you can just see here it going up and up and up, okay? Whereas the loss in an average house, the loss through the walls and windows and floor and attic, it's linear, right? It doesn't change, okay? It's the same house. So we've got the summer loss for cooling, and we've got the winter loss for the heating season, okay? And you can see here that really, there comes a point where if your house is really air leaky, and we've tested brand new houses at 7 air changes, which to me is very scary. My house in High Park, or in the Junction, when I first bought it, was in the 14 air changes. Proud to say that I'm down to 10 air changes. I've got a long way to go. Passive house, by the way, is less than 1, okay? So just to sort of give you a little bit of language and comparison, old double brick house in Toronto, 13 air changes. Average new house, 4 to 5 air changes, okay, in that range. Passive house, we're down to here, okay? So this orange line is something that all of you can control easily by just saying, hey, let's test the house. Let's make it airtight. And you know, when you invest in what is now a mandatory heat recovery ventilator, that heat recovery ventilator pays for itself in a tight envelope. There's nothing worse than installing an HRV in a crappy old leaky house, right? Why? We're air exchanging air in a house that's already getting a lot of air exchange naturally. So really, what you're doing is you're bringing greater value and you're making your heat recovery ventilator earn its keep. So for unwanted moisture to move, and moisture is something that we should all be concerned of in building envelopes, right? Nobody likes mold, nobody likes ice damming. So what are the 2 conditions? This is a Joe Stebrick question, okay? What are the 2 conditions that are needed for moisture to move through a thermal enclosure? What do we need? 2 things. Pressure difference, pressure gradient. Yes, thank you, 1 point. What else do we need? Don't be shy. Yes, yeah, if there's no humidity, then let it leak. Yes, no, you're right. There will be there's no, but the other thing that we need is yes. Stack effect is a gradient, yes. Yeah, so that's one. The other thing we need is a hole, right? In order to actually get moisture to move or energy to move out of building envelope, we need 2 things, really simple. We need a pressure gradient, we need a hole. And as you say, a stack effect is the biggest driver, is the biggest pressure gradient on our building envelopes. The next biggest one is usually mechanically driven. And so who here has clients who want a 6-burner Viking stove, gas? Yeah. So what do you have to do to install that? What's the code say about? You need 1,000 CFM exhaust fan. So when you fire that thing up, the front door kind of goes, it opens up, and you feel the air come in. And literally you'll get flame rollout in your open face fireplaces, which is something that we get calls for every once in a while. So remember this, a pressure gradient and a hole, that's all you need, okay? So Joe Stebrick's BSD 163, controlling cold weather condensation using insulation. Insulation, that should have continued, and air barriers. Cold weather condensation is primarily the result of outward air leakage. So air leakage from the inside migrating to the out, okay? And here's what I want to tell you. As we start to build tighter building envelopes, we're bringing up the relative humidity in the house. We're going to have more issues if in the coming years if we don't get it right. Let's make buildings airtight, okay? And I feel that's very important, because if you've got a house that has 35% relative humidity versus a house that has 55% relative humidity, and they're both leaky, I can tell you that the house with the 55% relative humidity is going to suffer. The building envelope is going to be more prone to mold, more prone to ice damming, more prone to members rotting inside the wall assembly than the house with the drier air. So just remember that. We're going to unintentionally build tighter houses as we put in continuous sheathing. And let's get the detail right, because it'll be less forgiving going forward, all right? So remember that. So diffusion usually does not move sufficient quantities of water vapor fast enough to generate a problem. So what do we mean by diffusion? So we've got a couple of different materials here. We've got Roxol. We've got this expanded polystyrene, right, where the old coffee cups are made out of the beadboard. And we've got SM. So essentially diffusion is the amount of air that moves through a material. This will diffuse a lot. Obviously it breathes quite a bit. This will diffuse quite a bit. This will, like a vapor barrier, will diffuse very little. So if we've got an air barrier in the house, an air barrier will behave somewhere between this and this, depending on what it is. Very little humidity will actually move through a substance, okay? What we're interested in is we're interested in the crack between those two pieces. The connection between the roof and the wall. The connection between the slab and the wall. And now we're making, remember, we're making more airtight house. We have to start thinking about radon as well. So that slab needs to be airtight as well. So to control damaging condensation walls and air roofs, air barriers are used to stop airflow, and vapor control layers are used to limit diffusion of flow. So essentially, Joe Steverick, what they've done here is, you can see in a regular 2x6 wall with insulation and a vapor barrier, this plane, this blue line here, okay, is essentially right here. So on this graph here, in the cold months of January, February, and March, there's the potential for condensation right here, okay, from December, you know, from Christmas all the way to March, you know, the mid-March. So that's the problem here. If we've got any gaps in our wall and any moisture is getting through cracks in that, we're going to get condensation on that. Now compare that to your wall with continuous insulation on the outside. If we've got a stud and we've got continuous insulation, now that continuous insulation is increasing the R value, or sorry, is increasing the surface temperature of that red line. That red line is a lot warmer now. So even if you have the same amount of air leakage, because it's warmer, you can see here that it just misses the condensation. So you can see that that continuous insulation is a little bit of insurance for the architect, for the designer. So an airtight envelope, more durable, has less moisture pumped through the envelope, saves money, lower utility costs, more comfortable, keeps humidity and more even temperature throughout, is less liability in terms of callbacks. We get callbacks, you know, I can show you reports of brand new buildings that look beautiful but perform very poorly where the homeowner is very angry. And those are sad stories. When somebody buys a new house, they invest a lot of money and things just don't work out. It's not nice to have to go back and do a diagnostic on trying to fix things, because things are very expensive to do, you know, after the fact. And I hope all of you guys are redlining your drawings. So the redlining is something that we're starting to see. All good architecture firms will show the builder where the air barrier goes. In this case, the air barrier is like a header wrap, a breathable header wrap like a Tyvek. Comes around, maybe it's a 6 mil poly here, and it converts into a header wrap, back to a 6 mil poly and a 6 mil poly here. So that's typical old school. Again, these are building science, thanks Dr. Joe. This is using the Typar or Tyvek on the outside, or even the blue skin. This is so this product here is a little bit different because it's self-adhere, an SA. The VP100, it's a self-adhered membrane. Yep. On the outside. This is a really beautiful, simple approach. We're right at the mud sill. We seal it to the foundation with a good bead. You can buy some great sill gaskets here, and you can just have a breathable air barrier all the way to the top. Really simple, and it transitions here to a 6 mil poly. Right? And if we carry that theory to insulation, whether it's vapor open or vapor closed, if it's thick enough, it can be vapor closed, like the blue stuff or the pink stuff. If it's really thin, we don't put a lot of it, then it might need to be vapor open, but you can still get a seal off of it. I would say that you can get a better, more continuous seal out of using the blue or pink because it's shiplapped. But yeah, I mean, you can seal that on the outside, and that becomes your air barrier. It's not, it's not your vapor diffusion layer. The building inspector will still make you put a vapor diffusion layer on the inside. At which point, I would argue that, you're right. I mean, why? We've got painted drywall, which is going to be a vapor diffusion layer anyhow, right? Yes, well, except that those screws are clamped, right? Those, the screw is actually going through the drywall and it's physically clamped to the wood. So there's not going to be a lot of air leakage through the screw. But I agree, at all the penetrations for plumbing, for electrical, and there's a lot of them, along the bottom plates, the top plates, you're going to see a lot of leakage, So this is the best way here. Put your air barrier on the outside and get it done with, you know? I don't know what it is in Ontario where we've got so many misconceptions about the poly and using the poly as an air barrier. It's a mistake.
The situation, where would be the condensation point?
The condensation point would,
The wall itself.
the condensation point would be the interface of the insulation right there. Okay? Let me back up. So where that red line is, that's the condensation phase, or that's where the potential is for condensation.
On the other side, otherwise it would just go down.
But the point is that there's actually no condensation that takes place. There's no condensation that takes place because it's warm. Okay? So, but I digress. And if any of you guys want to come and join me at the office for coffee, be more than happy to talk ad nauseum about this nerdy stuff. It's the kind of stuff we like. But just to give you an example here, so which air barrier, if we're using the 6 mil poly on the inside as an air barrier and a vapor barrier, so it's doing double duty, versus using a Tyvek on the outside, how many holes do you think you'll have on the inside versus the outside to seal? I'm going to take a guess. Let's say in the average house, if we count all the, all the fire alarms, the exit signs. Oh wait, that's not in the house. All the electrical plugs and switches. All the penetrations for HVAC. Maybe if the thermostat is foolishly on an outside wall, it could be a penetration. So let's say 58 holes to seal on the inside, and if I use my insulated sheathing or blue skin on the outside, there's only 16 holes to seal. And the plumbers can go to town, right? So all this to say that bringing things back to building for the future, FIAS 2015 Climate-Specific Passive Building Standard. In 2015, FIAS, the Passive House Institute of the U.S., came out with Building Science Corporation with research funding from Building America program, so the government of the United States. They came up with a climate-specific passive house standard for North America. They made a compelling argument why the Darmstadt, Germany climate was not a one-size-fits-all for Canada, okay? And for Florida, for the Everglades, for California, for Alaska, it just didn't offer enough specificity and required too much in certain climates. So in terms of the outputs that we can get, like I said, we can import the DWG files and start modeling the house right away. It's very exciting. The data that we can get from this is fantastic. Hydrothermal modeling, we can tell you what are the odds of condensation building up year after year. It's a very powerful, the Germans have really worked hard on this software and can tell you if year after year you're going to build up moisture. As opposed, you can find out, is my building assembly generally on a drying trend year after year, or is it generally on a wetting trend? Very important to, and especially maybe not so much in Toronto climate, but in maritime climate, it is very important. And also 3D thermal bridge calculations. So, certainly if you're using a lot of concrete slabs and you're using, a lot of steel in your designs, this could be a very powerful tool. So we're really excited to use that. I think I've talked too much. Thanks for your time and thanks for listening. Do you have any questions?